Can everyone see that okay? It should say unit 13. That's not correct. We're actually on unit 25, so that's wrong. Apologize for that. But yeah, we're doing unit 25 and 26 today, or at least the beginning of 26, which is further graphs and then an introduction to calculus. Now I'm going to focus more on the graph stuff because it's for everyone. It's for foundation and higher. I will do a little bit of an introduction into differentiation, which is higher tier only. So I apologize for those of you. I know there's a couple of you only studying foundation, and you can just completely ignore anything on differentiation if you choose to. So I'll let you know at that point. But the beginning half of this lesson will be important for anyone doing both foundation and higher. Okay, so any questions before I get started? Okay, let's get started then. So it's really important that you can recognize all the different types of graphs. Okay, so we did a couple of weeks ago, we did linear graphs, the straight line graphs, and we talked about how every equation can be represented on a graph. Okay, so it doesn't matter what like equation or function of like mathematics we're doing, there will be some kind of graph for it. And the different types of equations or functions will have different features. So you need to be able to recognize some of these graphs, okay? Just by looking at it, you need to be able to say, that's a quadratic graph, or that's a cubic graph, or that's an exponential graph, or something like that. So I'm going to go through today the different types of graphs that you need to recognize. And generally, it's looking at the highest power of x, okay? So whether it's just x on its own, or whether it's x squared or x cubed, that's what determines the shape of the graph. So let's have a look at, oh, I don't know why that's there, ignore that for the moment. Let's have a look at the couple of examples. So last time we looked at linear graphs. Linear graphs are straight lines. So we looked at examples like y equals 2x plus 1, okay? That's linear because its highest power is just 1, okay? That is x on its own is technically the same as x to the power of 1. So its highest power of x is just 1. So it's just basically a straight line graph, okay? It looks something like that. We did quite a lot of work on that last lesson, so you can go back and review that lesson if you need a bit more work on linear graphs. Then we've got quadratic graphs, okay? So quadratic graphs are curves and they have one turning point. So a quadratic function is something like this. It will be y equals x squared plus 2x minus 1. It could be anything that looks like that, where the highest power is 2, okay? So it will have x squared in it. It won't have an x cubed in it or anything higher because that will be a different graph, okay? So the highest power is x squared. And quadratic graphs look like this one here. So they're a curve, but they just have one turning point. So these 2 points will kind of continue going on up there, and this one will continue going on up there forever, like that, okay? And then finally, this picture down here is of a cubic graph, okay? So a cubic graph has 2 turning points. Technically, a cubic graph can have up to 2 turning points. I'll go into that in a little bit more detail. So you can see here, this one kind of comes up, and it turns, goes back down a bit, and then it goes back up. So that's a typical cubic shape graph there. And that will have an equation where the highest power of x is 3. Okay, so that will look something like that. You don't have to worry too much about being able to draw these if you're doing foundation. Just being able to kind of recognize the graphs is enough. So just looking at that and going, oh yeah, that's, you know, an x cubed graph, and this one is an x squared graph. So this is a cubic and this is a quadratic, that's fine. You may have to draw them from tables, and definitely in higher tier, you will have to draw some form of a graph from a table, where we did a bit on it last week, where you're given a table and the function, and you have to like fill in the table from the function and then plot the coordinates and then draw the graph. So it's definitely worth practicing doing that, just nice and neatly and accurately as well. So I'll just go through how you would do that. So you'll be given the function of the graph, okay? So you might be told And remember, if you're in higher tier, they may use function notation. So if you remember what the function notation was, they may use like f of x equals, and then they might say f of x is, I don't know, I'm going to say it's a half x squared minus 2. Okay, I've just made that up, doesn't matter. And they might ask you to draw that graph. So it's really important that you can almost kind of picture the rough idea of what it's going to look like in your head. You're not going to know that because its highest power is a 2, it's a quadratic. Okay, so you're going to think, oh, that's a quadratic, it's got one turning point. It's going to look something like that, because then you kind of know what your answer is going to be like before you even start. Okay, and then it will give you a table. So it might give you a table, and it will pretty much always have all of the x values filled in. That will be -3, -2, -1, 0, 1, 2, 3. And again, this could be in foundation or higher. Okay, and then you will fill in, not all of them, but a couple of these. There might be some answers there, and then some that you would need to fill in. So this -3 squared is 9, positive, not negative. Okay, divide that by 2 is 4.5, minus 2 is 2.5. So that would be at 2.5 there, and so on. You would just literally plug those in, do some substitution. Most likely you'd have your calculator. You'd be doing this in a calculator paper. So it's just simply, substituting the values in, generating the coordinates, and then plotting the coordinates. And you go, okay, well, at x is -3, y is at 2.5, at x is -2, so that's going to be -2 squared is 4. Divide that by 2 is 2, minus, oh, that's a 0 there, look, okay? And then you'd plot those graphs, and you'd get this shape here. Okay, so it's just really good to be able to think before you even start, okay, I know what this graph is going to look like. Same with a cubic. You might have been given f of x is -2x cubed minus 3x plus 1, or something like that. And you're going to say, well, the highest power is cubed. So this is going to have most likely 2 turning points, okay? So it's not going to be like this or like this. It's not going to be a straight line like this, okay, because it doesn't fit those shapes. It's actually going to have 2 turning points. And because this is minus, this one technically would have 2 turning points like this. Okay, so it will go in that direction, which I'll talk about a little bit more in a moment, okay? But you know that it's going to be that shape. And then again, you'd fill in your table, get those coordinates, see that it is that shape, and be happy with the fact that you've got it right, or very likely got it right, okay? So if you had an x cubed and then your final answer looked like this, you'd be going, oh, I've probably done something wrong here, because that's not a cubic shape, okay? So you know that it's really good to do that, okay? Right, so that was kind of how to plot the graphs there. So use the function to find any missing points, plot the coordinates carefully, and honestly do, because the exams, they have quite a lot of marks for just plotting those coordinates. So plot them really carefully, be really accurate about it. Okay, spend some time really making sure that you're putting your little X's in the right place on the exam paper, because they're normally about 4 or 5 marks for getting those right, which can be up to a half a grade, can't it? So it's really important. And then join them up nicely with a nice smooth curve. Check that, the features of the graph you've drawn match the features of the graph, the function you've been given, okay? Right, so a quadratic function. A quadratic function, we've done some work on quadratics, is in the form y equals ax squared plus bx plus c, okay? So it's going to look like that. What I'm going to do actually is I'm going to do something I don't normally do and share a different screen with you. Just a second. I'm going to just get some graphing software up and just show you how you can use graphing software at home. So let me just share this with you instead. Okay. So hopefully, just give me a nod if you can see the graphing software Desmos right now. You can, excellent. So this is literally just desmos.com. Okay, if you just type in desmos.com/calculator at home, you can actually just start looking at some different graphs and how they behave. And I just think it's really useful just to get used to sort of seeing how different graphs behave. So there we go. I've typed in y equals x squared, and you can see that sort of shape there. Okay, so that U shape there. If I change that now to be y equals x squared minus, let's say, 4, you'll see how it's moved down and it's now going through that y-axis at -4. So it's just really like literally just play with the graphs and just see how they move as you change their functions. If I change that to be +4, hopefully you'll see, and hopefully you will have guessed, it will go up to be going through the y-axis at +4 there. Okay. What happens if I change this instead of being y equals x squared? Let's make it y equals x cubed. Okay, so y equals x cubed +4 keeps going through the y-axis at 4, but now it's got that cubic shape. Okay, what about if I change it to y equals x cubed plus 4x minus 3? You can see it's really stretched out and it's now going through at -3. So I recommend spending some time, just get a really simple graphing software app. I like Desmos, it's really easy to use, and see how graphs fit. And you can use this when you're practicing your GCSEs at home. You're doing a paper and you've been given a graph like this. You can have a look on this and you can actually type it in and you can see what the graph is meant to look like and use that. Okay, so that's really good. I'm going to come back to this later, because I want to do a bit on actually using graphs to solve equations as well. So we will come back to this in a moment, but I'll go back to my PowerPoint for now. Does anyone have any questions on that? No? Okay. Oh, no worries, Meadow. I just saw your message in the chat. No problem at all. Nice. Thanks for joining us. Okay, so quadratic functions in that form there. So we've just kind of seen what they look like. A positive quadratic is a smile shape. Okay, I always think of the positive ones. They're smiling because they're positive. And positive means that the A is positive. Okay, so basically the number in front of x squared, the coefficient of x squared, if that's positive, then it's always going to be a graph that goes that way around like that. Okay, the smile shape. And a negative quadratic, so if A is negative, it's going to be a rainbow shape. I used to call it a frown shape, but I've decided to start calling it a rainbow instead. So it will be that shape. Okay. So those are the negative ones. Okay, so that's just a really important feature. You might have noticed when we were looking at Desmos that the C value tells us where it goes through the y-axis, is the y-intercept, exactly the same as when we did our linear graphs last time, and it was that C value that goes through the y-intercept there. And of course, that's really easy to see because on that y-axis, the x value will be 0, okay? If it's going through y, then the x value is just at the point where x is 0, okay? So that basically shows us that if I put 0 into the x's there and there, all of this becomes 0. So the only thing left is C. So that's the point at where it cuts the y-intercept. So if you are given a graph and you're asked to draw it, you really need to look at what the value of A is. Is A positive or is A negative? And you need to look at what the value of C is, because that tells you where it goes through the y-axis. Okay, so that really helps with drawing these graphs. Okay. They're also symmetrical. Quadratic graphs are always symmetrical, and they have obviously their turning point. Their turning point is also called their minimum or maximum. Just, if it's turning at this point, it's the minimum point of the graph. If they're turning at this point, it's the maximum point of the graph. Next lesson, so in 2 weeks' time today, we're going to be doing lots of work on finding these minimum and maximum points, okay? That finding those points is higher tier only. So if you are foundation, I'm afraid it's going to be quite a lot of higher next lesson, because we're going to be focusing in on kind of the calculus behind graphs, really looking at these. But it's really good just to understand that, the minimum point is the line of symmetry. It goes through that line of symmetry there on a quadratic, okay? And also they will have either 0, 1 or 2 roots, and that depends on how many times they go through the x-axis. So roots are just where the answer if y equals 0 is, okay? So let's imagine I'm just looking at y equals x squared, which we looked at on Desmos a minute ago, and it's just literally this graph here, if you pretend that's nice and symmetrical and goes through the origin there. Okay, that's got one single root. It goes through the point, the origin at 0, 0. I'm not doing a very good job of showing you. I'll show you on the Desmos thing again, just so you can see it. So let's get rid of that and just look at the graph of y equals x squared. Okay, so you can see that it just goes through, just has one kind of what's called a root. That's where it hits the x-axis, and it's at that point 0, 0. Okay, so it's just got one solution. And if I wanted to find the answer, I wanted to find what the answer is, y equals 0. So I would find 0 equals x squared. Well, the answer would be at this point square root of 0 equals x, which is just 0. So I can see, sorry, we've not solved that very well, that x equals 0 is my only solution there, okay, to the point where x squared equals 0. If I now considered thinking about the graph y equals x squared minus 3, for example, okay, you can see this goes through the x-axis twice. It's got two solutions, or two what we call roots, all right? And those solutions are there and there. And actually, the solutions are at the square root of 3 and the square root, or the negative square root of 3. And again, if we considered solving this, so if I said, okay, we'll solve x squared minus 3 equals 0. So if I let y equal 0, then I would first of all bring this 3 to the other side. So I'd solve the problem x squared equals 3, just solving the equation. To solve this, I'd now have to square root both sides. So I've got x equals the square root of 3. And of course, when you take the square root of something, when you're solving an equation, you need to consider the fact that it could be positive or negative. So we could have two possible answers there. And that's why we've got two solutions. We've got the solution minus root 3, and we've got the solution positive root 3 there, okay? And let's just consider one more just to really show that again. Let's consider x squared minus 16, okay? So you can see now it's gone all the way down, this y coordinate's going down through at negative 16. And hopefully you can see, if I zoom in there, the solution is at minus 4 and positive 4. Okay, so the graph is going through at the positive and negative square root of 16 there. Okay, so again, solving these ones are quite nice and easy because they don't have that middle term. I'm doing that on purpose. X squared minus 16 equals 0. So if I solve this now, x squared equals 16. So x is going to be the positive or negative square root of 16, which is either plus or minus 4. Okay, so I've got those two solutions there. So those 2 points there. Okay. Anyone have any questions on this so far? Giving you lots of information again. No questions? Okay. All right. So that is, you've seen an example of having just one solution where it just touches the x-axis. You've seen lots of, or a few examples of having two solutions. And there is also a possibility that it could have no solutions. You don't see many of these at GCSE because there's not that much you can do with them. But you will occasionally get graphs which don't hit the x-axis at all. They actually float over the x-axis like this, okay? They don't have any solutions at all. They don't have any solutions in the real number system anyway. And we don't worry about any other number systems until you get to quite further maths A level. So you don't have to worry too much about those ones, but you do have to know about their existence and know that they can possibly have no solutions, okay? So you can see that one floating up there. Okay, so those are examples of your quadratic graphs. And that's hopefully something you'll be able to recognize. We've talked about solving them now, okay? So solving them is literally just looking at the point where y equals 0. So solving this y equals x squared minus 9, let y be 0, and then look at where it hits the x-axis. And you can see, hopefully, if you've worked it out in your head, you can think, well, if y is 0, then x squared equals 9. So x is going to be 3 or minus 3, okay, because it could be positive or negative square root of 9. And so you can see, hopefully, here, minus 3 there. Minus 3 there and positive 3 there, okay? You also do get, and again, this is more sort of higher tier than foundation. You could also be asked to find the solutions of the two graphs or the two simultaneous equations, something like this, y equals x squared, and the graph of y equals 9. And so what you can see is I've done here is I've actually plotted the graph of y equals x squared, and I've also plotted the linear graph y equals 9, okay? Do you remember we did our straight line graphs last time, and those horizontal graphs like this, just where it goes through y at 9? So you could be asked to plot a straight line graph over a quadratic graph. And if you are asked to do that and to solve the simultaneous equations, you are literally just looking for the points where they meet, okay? So they meet there, okay? So you would then just follow that down. Ooh, probably using a ruler would be a good idea. And find the points on the x-axis. So you can see there it's minus 3 and positive 3 there, okay? So you can see that's solving that graphically. If you were going to solve the simultaneous equations, y equals x squared and y equals 9, not graphically, if you're just going to do that algebraically, you would do that by putting them equal to each other, wouldn't you? You'd eliminate y here, and you'd just say x squared equals 9. And then you could say, well, that's the same as x squared minus 9 equals 0. So you can see that the solutions are the same, which is why this graph x squared minus 9 has the same solutions as the points where the graph x squared and y equals 9 meet each other, okay? So it's also something that you can have a play with on Desmos as well. So I will go back to Desmos. I'm going back and forth a lot today. But you can have a look at solving, and especially if you are doing higher tier, I would highly recommend that you do spend some time. Let's just put a graph in. So here is a quadratic graph, y equals x squared minus 3x plus 1, okay? It's got two solutions here. It's got a solution at this point and a solution at this point. I've put this middle term in, which is why it now is a little bit further over. It doesn't go, it's not got the line of symmetry at 0 there, but it's still, you know, your typical quadratic. And so you might have this, you might have, you know, your part A and B in an exam might have been to plot this graph. And so you might have filled in a few points on a table, plotted some coordinates and drawn this graph. And then you might get point C, part C. And part C might be to draw the graph of y equals 2x minus 1 or something like that. So to draw a linear graph over the top of it. And so you would draw that just from your knowledge of linear graphs, which we did last time. And you'll see that they have 2 points where they actually meet, okay? And then the question, parts D, might say to use the graphs to solve the simultaneous equations, this and this, okay? So to solve them simultaneously means basically to find the points where the x coordinates are the same, okay? And you would do that by simply looking at where they meet. So on Desmos, it's really nice and easy because you can click on it and it'll tell you. So they meet at x equals 0.438. And they also meet right up here at x equals 4.562. Okay, so you can find those points. In your exam, you would probably have slightly nicer numbers. It probably wouldn't be to three significant figures there, or 3 decimal places, but they sometimes do have horrible numbers, in which case you get a range of answers. So as long as you get it between like 2 sort of fairly close numbers, then you get it right. If they are a bit strange like that, make a really big deal of finding the points where the 2 graphs meet, and then just bringing them up to the x-axis and reading off that point on the x-axis, so the examiner can see that you have done the correct method, okay? So it's just finding the point where the 2 graphs meet, and then finding the x-coordinates, reading it off the x-coordinates. Does that make sense? Do you want me to go through another one? I feel like I've done that quite quickly, or are you happy with that? No? Okay, I'm going to assume that that's okay. Move on to cubic graphs, unless anyone wants me to go through anymore. Okay. All right, so cubic graphs. Okay, so cubic graphs, they're in this form. So they have ax cubed plus bx squared plus cx plus d. Okay, so they'll look like something like that. A cannot be 0. B or C can be 0. I should have said that with quadratics as well. So here, A cannot be 0, but B could be 0, or C could be 0, okay? So a positive cubic goes from bottom left to top right. So if A is positive, it will look something like that, okay? And then a negative cubic goes in that direction like that, okay? So just kind of the same as linear graphs, a straight line graph. If the gradient is positive, it goes that way. If the gradient is negative, it goes that way. So it's the same direction. It will just be a curve rather than a line. Okay. So that's what they look like. They can have up to 2 turning points. Okay. Or if they don't have 2 turning points, then they could have something called a point of inflection. And I think you saw that with the graph y equals x cubed, which is here. So a point of inflection means that it just kind of goes horizontal for a moment and then carries on going up like that, okay? So it's not technically a turning point because it hasn't changed to go negative. So it's not gone, down and then up again like that. It's not actually been a maximum or a minimum, but the gradient has just gone horizontal there for a moment. So the gradient is 0 at that point there, okay? And then they also have either 1, 2, or 3 roots. Okay, so remember the root is the point where it crosses through the x-axis. Okay, so it could cross through just one time like this one here does, or it could go up and then back down. Okay, it can't have 3 roots. My apologies, that's not correct. It either has 1 or 2 roots. Sorry about that. Just realize that that's not right. Okay, I'll change that later. But yeah, no, ignore that last part. They can have 1 or 2 roots. I'm very sorry. I'm just thinking they can go up. Oh no, they can have 3 roots. What am I talking about? Let's have a look at Desmos. So let's have a look at some examples here. So let's make this x cubed. There we go. There's an example. 1, 2, 3 roots. Okay, so they absolutely can cross over 3 times. Okay, or they could cross over. If I could bring this, make that like 2. Oh, that's a good example. This one has 2 roots. I think that one goes through there, but then it just touches there. So that's 2 roots, and then there just 1 root. Okay, so they can have 1, 2, or 3 roots. Okay. They have to have at least 1 root though, because they have to cross through that at some point, because this will keep going down and this will keep going up, okay? Whereas the quadratic could be completely above or completely below the x-axis. A cubic will go all the way, go through it at some point, okay? So that's what a cubic looks like. Did I just share that with you? No, I didn't. I'm so sorry. Let me do that again. Just realized I just did it and then I didn't share. Okay. This is what I was trying to show you. Can you see it now? Yeah, I'm so sorry. Here we go. Right. So this one is just a one root one, okay? Because it goes through that x-axis at one point. Okay. I think when I had it at 2, there we go. If I change that to 2, you can see it's got 2 roots. There it goes through, and here it just touches the x-axis. And then if I make that less than 2, so let's make it -1, you can see it's got 3 roots there. Okay. So apologies for that, everybody. Just trying to show you something and I didn't share it with you. Any questions on those cubic graphs? I will just also show you while we're here. If I make that negative, you can see it changes direction. Okay. So again, it's a really good idea just to kind of play with them. What happens if I add in the squared there? So you can see now it's got 1 root is going in the negative direction because that's negative there. Okay. And it's got 2 turning points. So all these features are just really important to be able to recognize. Okay. Back to the PowerPoint. Okay. So cubic graphs were that, and then the other one that you might, or you probably will have to come across, especially if you're doing higher, is reciprocal graphs. And reciprocal graphs are where you have y equals a over x or y equals a over x squared. So either one of these ones could pop up. And you can see, I think we talked a little bit about domains when we did the functions lesson. So a domain is basically the input of the function. So it tells us what can go into that function. And you can see that because we're dividing by x here, we cannot have the input x is 0, okay? Because you cannot divide by x, divide by 0. If you try and divide by 0, you just get an error message on your calculator, okay? Because you cannot do it, cannot share something between nothing. So we have to say that x is not 0. And that becomes really important in the graph because we cannot put the value of x is 0 into the graph. So we have something called an asymptote at this point. If you heard the word asymptote before, it might be new to some of you. An asymptote is basically a line on a graph where the graph will get closer and closer and closer to it, but it will never go through it, okay? So this graph here has both the x and the y axes as asymptotes. That graph will get closer and closer and closer, but it will not go through the x-axis. It will just get forever closer, okay, as x gets bigger and bigger here, or smaller and smaller here. And then again, as x gets negative, bigger and bigger, or smaller and smaller, I should say there. And then as it gets closer there. So those lines are called asymptotes there, okay? And that's because x and y cannot possibly be 0 in those graphs. And then think about what might happen if I had 1 over x squared. What would happen to this negative side if I squared all of those values of x? What happens to a negative number when you square it? What does it do? I can see someone typing. Yes, excellent. Well done. Thank you. Yeah, brilliant. Okay, the negative number becomes positive. So what happens if we try and square that x squared there? Okay, well, it's going to flip over and be a reflection in the x-axis because you cannot have a negative number there. Okay, so that is the graph of 1 over x squared. So that again has the asymptote there at the y-axis and the x-axis. It's kind of hard to see that it's an asymptote, but it is. It looks like that red line is touching the axes, but it's not actually. It will never actually touch that axis there. Okay. So these graphs are literally just something you will need to be able to recognize. You might get one of those kind of A, B, C, D, like multiple choice questions where it asks you to match up the graph with the equation. And this is the kind of thing that you'll be looking for. So if it's that shape, you know it's going to go with an equation like this. Okay. So hopefully that gives you an idea of all the different types of graphs. Okay. So I'm going to talk a little bit more about gradients of graphs now. And we did quite a lot on gradients of straight line graphs last time. Ooh. No, that's a really good question, Meadow. Thank you. So Meadow just asked, are asymptotes always getting closer to both axes, or can it be just one? It can definitely be just one. And also, I am actually going to answer that by sharing with you another Desmos. And it can also be any line. It doesn't have to be an axis. So let's just plot the point 1 over x here. So you can see as that goes, it looks like it's touching, but it will never be touching. If you zoom in, it will never touch. But that's 2 axes there. But what happens if I put like +1 here? You can see actually now the asymptote has moved up to be on the y-axis at the point 1. So if I zoom in, this is the point 1. The asymptote is now 1, okay? In fact, it's easier to see that if I draw the line for you, y equals 1. So if I put that line y equals 1 in there, now it's getting closer and closer to the point where y equals 1. And the reason why is because we still cannot have x is 0. We still cannot put x as 0 because we'd have to divide by x. But y now, okay, we cannot have the point where y is 1, because if x cannot be 0, we cannot get 1 divided by 0 plus 1, which is what 1 would be, okay? So that's why that jumps around, and that will happen with all graphs. We're not doing trigonometry at the moment, so this is completely just going on a tangent here. It's funny that I said tangent because that's the graph I'm going to show you now. But the graph of y equals tan x has loads of asymptotes. It's got no asymptotes horizontally, but it has asymptotes at every point where, let me see if I can change this to degrees. Okay, I don't know quite how to change this to degrees right now, but this point here, if this axis had degrees on it, would be at the point 90 degrees, okay? Because if you try to do tan of 90 degrees, you'll get an error message on your calculator. And that's because tan of 90 degrees is not possible. So it'll go all the way up and all the way down, but it will never actually touch that line. So you can see loads of asymptotes there. It's not very easy to see them. Normally, if we draw the graph of tan, you would actually draw in the lines, the asymptotes there. So trying to remember, that's hard for me to do right now because it's not in the right format, but you would draw the lines in and then you would show this line getting closer and closer. And then here where it's sort of met and get closer and closer down there, okay? So that's just another graph that has an asymptote. Another graph that has an asymptote is the graph exponential graphs. E to the x gets closer and closer here to the x-axis, but we'll never go through it, okay? So again, we don't really need to focus on this too much, but it's just to be aware. So lots of graphs do have asymptotes, but they could be anywhere on those axes, okay? And there could definitely just be one, or there could be lots, right? Does that answer your question? Love getting questions. Makes me feel like everyone's listening. Yes, good. Okay. All right. So gradients of graphs. So we did gradients of straight line graphs last time. Okay. So just a quick reminder of that, because that's important. Everybody needs to make sure that they're really, really familiar with finding gradients of straight line graphs. You would take the straight line graph, you find 2 coordinates, which I've already done here, draw that triangle, count the difference in y, so the rise, which is 4 units, count the difference in x, which is 2 units, and then you'd say the gradient, which we always called n, didn't we, is rise over run, or the difference in y divided by the difference in x, which I think I've written up here. There we go, change in y divided by change in x. So on this one, it's 4 divided by 2, which is 2. Okay, so this gradient, this straight line has a gradient of 2, and it has a gradient of 2 all the way through it because it's a straight line. Okay. However, so a gradient of a straight line is always the same. It's never going to change because it's just a straight line. However, with a curve, the curve is always changing, which means the steepness of the curve is always changing, okay? So we cannot just sort of we can't just find the gradient of a curve and say it's a number, because it's always going to be different no matter where you are. What we can do, okay, oh, hang on, instead the gradient is an algebraic function, which we're going to learn in a moment how to find. And to find it, we need to differentiate, which is higher tier only, okay? So if you are doing foundation, don't worry about learning differentiation. You don't need to worry about it. But what you can do as well, before you do go away with your foundation, or, you feel free to stay, but is you can draw a tangent to the curve at any point. And a tangent is just a straight line that touches the curve at a point, okay? So I could draw a tangent to a curve at basically any point. I could say, I want to find the gradient here. So I'll draw the tangent, and then I'll just use that technique that we just did. I'll do that. I'll find the difference in y, and I'll find the difference in x, and I'll find the gradient. And that would give me a number that is the gradient at that point, but it would only be the gradient at that point. It wouldn't be the gradient here or here, because the gradient's always changing, okay? So you can see on this graph, it's quite steep and positive here. That was a bad drawing, but if I draw a tangent there, it will be quite a steep, straight, positive line. If I draw a tangent here, not as steep. If I draw a tangent here, it's negative now. That wasn't a tangent. I'm very bad at drawing with this pen, because the tangent touches the line and does not go through it. But you see the point. So it's negative. Up here, again, much steeper. So it's always going to be changing, okay? So we cannot just use that technique and find the gradient. Instead, we will find the gradient function, okay? And so that's differentiation. So if you are doing foundation and you want to listen, please feel free to carry on listening and just learn something. But if you don't want to, I totally understand. You might have something better to do with your evening. So absolutely fine for you to switch off now if you'd like. But let's learn how to differentiate. So if I take the graph of y equals x squared, and I look at taking a tangent, say here, okay, you can see that my gradient here is just going to be 0, because that tangent is horizontal. Let's imagine I take the tangent and I draw it here. And I wish I could draw in a really nice straight line here, but I can't really. If I wanted to find the gradient here, I would draw the straight line. I would put a horizontal, and I kind of do this. Oh, really badly done, but sorry about that. There we go. That's what I was trying to do. And that straight line will have, the triangle will have the x difference in x will be 1 there, and the difference in y will be 4 there, okay? So this straight line here, the gradient at the point where x is, you can see x is 2 there, is going to be 4/1, which is 4, okay? If I did that here at the point where x is 1, I'm going to do that with a different color because it's already getting very messy. So if I did that here, the point where x is 1, okay, so I now want to draw a straight line with that tangent, okay, I want to go along 1, and it should go up to 2 there, so that goes along 1 and up 2. So at this point, the gradient m is now the difference in y divided by the difference in x, which is 2/1, which is 2. So you can see at the point where x is 2, the gradient is 4. At the point where x is 1, the gradient is 2. At the point where x is 0, the gradient is 0. At the point where x is -1, okay, that's where x is -1. Gradient there, you might have guessed it already, but it should be, if I was to draw a perfect straight line, okay, and if I was to do my gradient, it would be -2, okay, so at where x is 1, m is -2. And where x is 4, x is 2, m is -4. Where x is 3, let's find 3, or let's find 3 here, 2, 3. which is all the way up here, you can see it's already got really steep. At that point, the gradient is going to be 6. At the point where x is minus 3, the gradient is going to be minus 6, okay? And that's because the gradient function of the curve y equals x squared is the function y equals 2x, okay? So the derivative, it's called, which is the same as the gradient function, is y equals 2x. Okay, but you don't want to have to be drawing all these tangents every single time you need to find the gradient function. Luckily, there is a much easier method, and it's called differentiation, which is basically an introduction to calculus, okay? So quite newly introduced to the syllabus, I think. It's not been in the syllabus for that long, GCSE. So finding the gradient function, okay? Gradient function of the curve y equals x squared is the function y equals 2x. Gradient function of the curve y equals x cubed is the function y equals 3x squared. And in general terms, the gradient of function of the curve y equals x to the power of n is the function y equals n x to the power of n minus 1. Which feels like quite a lot to remember, okay, but it's not too hard to actually remember it. If you just remember the pattern, it's actually really easy to do. Gradient function of a single number is always 0, okay? So if you consider the graphs that we looked at earlier, you know, when we were moving them around on Desmos, so we had y equals x squared, and then if we did y equals x squared plus 2, it just jumped up 2, but it didn't change the graph in any way. It moved the graph, but it didn't change it. So that y equals x squared and y equals x squared plus 2, this number here doesn't make any difference to the shape of the graph. So it's not going to affect the gradient in any way, okay? So it doesn't matter just a constant, just a number like that on an equation, the derivative of that is just 0, okay? The only gradient is only affected by anything with x in it, okay? So we can only need to worry about differentiating anything with x in it. So how do we do that? We use that formula that I just said. We actually are just going to use the pattern, okay? Because I think the pattern is much easier to do. The gradient function of the curve y equals 3x squared is the function y equals 6x. Gradient function of the curve y equals 7x cubed is the function y equals 21x squared. Hopefully you can see a pattern here that emerging of how we're getting these numbers. 3 times 2 is 6. 7 times 3 is 21, okay? And then the x squared, it reduces, the power reduces by 1. And as long as you remember those two things, you can differentiate any kind of term like this. The gradient function of the curve y equals a x to the power of n is the function y equals a n x to the power of n minus 1, okay? And I'm just going to write this down for you. So I'm not going to prove this to you because you don't actually need to know the proof, and we really don't have long enough to do it, okay? But if you do want to know the proof, do feel free to go and watch some videos on it as to where it comes from. But essentially, what you do is if you have y equals a x to the power of n, you take the power, you multiply it by the a, and then you reduce the power by 1, and you get the derivative. And we call it dy by dx. Just comes from changing y by changing x, exactly the same as of linear functions. It's the gradient is the difference in y divided by the difference in x, okay? So that's all you need to worry about that. But that's what we call it. Dy by dx is always going to be a times n times x to the power of n minus 1. So you just think about that pattern, bring the n down, times it by the a, and then reduce the power by 1. Okay. And I think it's just easier to be seen in lots of examples. So I'm going to show you an example here. Okay, so if we are differentiating y equals 3x squared plus 2x minus 1, the derivative dy by dx, so this is the gradient function of this, it's going to be bring the power down and times it by the number in front of x. So 3 times 2 times x to the power minus 1. So times x to the power of 2 minus 1. Okay, you don't even need to go through all of this every time. You can just do it all in your head. I'm just trying to show you the slower kind of technique. So that bit there is just going to be 6x to the power of 1, or just 6x. And then here, okay, now this is 2x to the power of 1. So we're going to bring that 1 down and times it by the 2. So it's going to be just plus 2. And then we reduce the power by 1. So x to the power of 1. If we reduce that power by 1, we've got x to the power of 0. And x to the power of 0 is just 1. So that will just go away. There's 2x to the power of 0. But x to the power of 0 is just 1. So it's just plus 2. Okay. So a few things to remember. The things to remember are any constant, the derivative, any like constant like that, dy by dx is just 0. Any term with just x in, dy by dx is just the number without the x. And then any term with a power in, bring the power down, times it by the number, and reduce the power by 1. So we've got 6x here. Those are the things you need to remember, and then you can differentiate anything. Well, maybe not anything, but anything in those forms. Okay, let's do another example. I'm going to do that. I'm going to do this one first. Okay, so we've got loads of terms here, all very similar. So let's just use that pattern all the way through. So I'm going to take this power 4 and I'm going to bring it down and times it by the 5. So I've got 20. And then I'm going to reduce the power by 1, x cubed minus. I'm going to take this 3 and I'm going to bring it down and times it by the 3. So I've got 9x squared plus, I'm going to take this 2, bring it down and times it by the 2. So I've got 4x and then reduce that power by 1. So it's just x. Now, if I reduce that, so that's going to be to the power of 1. So it's just going to be 1x to the power of 0. So it's just going to be 1. And this one just goes away. How's that for differentiation? Does that help a little bit? If you think about the pattern rather than trying to apply the formula, it's a lot easier to do. Okay. And I should have put my dy by dx there just to make that correct. Okay. I'm going to come back and do that second point in a minute. Oh, no, I'm not, because I've run out. Let's get that back. There we go. Okay. Do you want to do just one more example? Let's differentiate. Does anyone want to give me something to differentiate as an example? Write something in the chat. No? Okay, that's all right. Okay, so I'm just going to pick some random numbers. I'm going to make this one a negative, minus 3x to the power of 7 plus 2x to the power of 5 minus 4x plus 9. Okay, so here times the 7 by the minus 3, so dy by dx is going to be minus 21x, reduce that power, so to the power of 6, plus 5 times 2 is 10, x, reduce the power to the power of 4. Now this just becomes minus 4 because the x is just to the power of 1 there, and then this 9 just disappears, so it should just be that. Okay. So that's that. And then we've got 5 minutes left. So I will quickly go through these examples. So if we are asked, quite often we're asked to find the gradient of a function at the point where x is something in particular. Okay, so that just means find the gradient function and then substitute that value of x into it. Okay, so to do that, we need to differentiate again, which I did, but we'll do it again. So it's going to be 5 times 4, which is 20, x cubed minus 9x squared plus 4x plus 1. Okay, so just differentiating this. Then we're going to substitute x equals minus 1 in, okay, to that gradient. So we're going to have 20 times minus 1 cubed minus 9 times minus 1 squared plus 4 times minus 1 plus 1. So that's going to be minus 20, minus 9 times positive 1, which is just minus 9, minus 4 plus 1, and it's all negatives, which is great, minus 29, minus 33. I think that should be minus 32, negative 32 there. Very, very steep at that point, okay? Anyone have any questions?